Hello everyone, we are starting with fluid kinematics, that is second part of module number 2. Okay, in module number 2 we have all this syllabus, of which we have done the first part, that is hydrostatic forces on surfaces, definition, total pressure, center of pressure, total pressure on horizontal, vertical and inclined plane surfaces, total pressure on curved surfaces, water pressure on gravity dams, log gates, and numerical problems on that. Gravity dams in the sense vertical surface with hydrostatic pressure diagrams we have done. Log gates is similar to all these problems only, with maybe hinges etc. will be there. So we have covered this particular syllabus already. Hydrostatic forces part 1, 2, 3, 4, 5. Now we'll be covering this part, though it looks large. It is not so much, but it is more dependent on mathematical knowledge of yours. So it is introduction, method of describing fluid motion, velocity and total acceleration of the fluid particle, types of fluid flow, description of flow pattern, and further things. So in this particular part or session, I'll be discussing up to types of flow. So this is what the syllabus is for fluid kinematics. I'll be discussing up to description of flow pattern, or only up to types of fluid flow as the time permits. Okay, so types of fluid flow. Now in this I'll start with defining kinematics. What is kinematics? It is branch of mechanics. So what is mechanics? It is nothing but study of forces. In this we studied resolving a force into components, finding a resultant of forces, equilibrium of force system, conditions of equilibrium like sigma fx equal to 0, fy equal to 0, and so on. So that is what is studied in mechanics, in the sense part of your introduction to civil engineering, elements of civil engineering. In that you have studied in length this particular part. Hope you remember all those things, like given a force, its resolution equivalent into vertical and horizontal components. That is, if you know the force as F, and then the inclination maybe with one of the components is theta, then we say that this is F cos theta, and that will be F sin theta. That is resolution. And then if you got number of forces, how to reduce number of forces into a resultant, like you will be doing sigma fx and then sigma fy. Using sigma fx and sigma fy, you will be finding out, of course this is sigma, will be finding out resultant and inclination of the resultant with one of the references as alpha. So this also you have studied. Then finding resultant or equilibrium of force system, that is drawing a free body diagram and putting conditions of equilibrium like sigma fx equal to 0, sigma fy equal to 0, or if it is a coplanar non-concurrent force system, then there is an additional condition of equilibrium sigma m equal to 0 also, right? So that is what is mechanics. But the mechanics is broken into two parts broadly: statics and dynamics. What statics does is, you can just see here as I have written, study of forces acting on stationary object or an object with constant velocity. Of course you have already done sigma f if it is equal to 0. I'll try to show you. Already we have done this part. If sigma f on a particular object is equal to 0, that is to say resultant is 0, but this is equal to the force equal to mass into acceleration. So that is equal to 0. Because m is not equal to 0, obviously a is equal to 0. So if the force system is leading to equilibrium, and then if the object is still in motion, then obviously we say that a is equal to 0, that is constant velocity motion. So in both the cases, if the body is not moving or if the body is moving with a constant velocity, it is domain of statics, where conditions of equilibrium are valid. In the sense, you can apply sigma fx equal to 0, sigma fy equal to 0, sigma m equal to 0. When it comes to dynamics, study of forces acting on the objects with accelerated motion, means a is not equal to 0, then f comes into picture. What are the forces which will be coming into picture? That is also we are going to study in further syllabus of fluid mechanics. Okay. Now in dynamics, we have kinematics and kinetics. There are two parts. Now kinematics means, look at this, it is only geometry of motion with respect to time is studied. That is to say, geometry of motion in the sense the distance with respect to time, or the curve that it has traced, because in projectile and all you might have seen that it is a parabolic curve that it traces, or a trajectory of motion you have called it as. So those things with respect to time, when you study only geometry of motion with respect to time, that is distance time relationship. Now if you say a rate of change of distance with respect to time, we call it as a velocity. A rate of change of velocity with respect to time, we call it as acceleration. And then the path traced by the object. So all these things are domain of kinematics, right? So velocity, acceleration, position, trajectory, everything is studied in kinematics, right? So how to remember is this particular m in kinematics. Here it is missing in kinetics. So it is only pure motion study. Motion, you have already studied this part in earlier subjects. So if it is a study of only motion of the object, then it will be kinematics. But if we have forces also into picture, that is kinetics, the forces causing the motion are also involved in the analysis. Means the major equation which comes into picture here is F equal to ma itself, because F represents sigma F, or resultant force, which leads to some kind of acceleration. So this equation is the major equation as far as kinetics is concerned. So now in this particular session we are going to concentrate only kinematics. Okay. Now kinematics, we are not going to study rigid body kinematics. You have studied already that in your earlier subject of elements of civil engineering. In this particular subject of fluid mechanics, there is a chapter kinematics, under which we are going to study hydrokinematics. Hydrokinematics means what? It is study of geometry of motion of fluids with respect to time. Again, geometry of motion with respect to time is kinematics of the flow. That is hydrokinematics. This defines motion of fluid in terms of space and time relationship. So here this will be telling you, this hydrokinematics will be telling you about space-time relationship, because in case of rigid body kinematics, generally what happens is we have considered planar motions. In planar motion only there was a rectilinear motion and then curvilinear motion, or pure rotation also, right? All those things are in plane. Space motion we have not studied, but when it comes to fluids, obviously you cannot talk about only one plane, right? Fluid flow, when it occurs, example would be a pipe flow. So when there is a pipe flow, obviously it will be having a size, a cross section of the pipe. If you take, maybe if it is a circular one or square one, the flow is occurring everywhere. So it is a three-dimensional flow. You cannot talk about a flow in one plane. So that is how the flow occurs. So flow of this particle, that particle, everywhere there is a motion. So it is a space time relationship. Another example would be, suppose there is a river flow. If this is the base of the river and then the flow is occurring, right, the top surface of the flow is like this, and then the flow is occurring with this. So there may be surface will be undulating here and there, the depth is changing here and there, the velocities are differing here and there. So all these matters will be studied in hydrokinematics. So it is drastically different from rigid body kinematics. Okay, we'll see further. Kinematics of solids is simple because relative position of molecules is not changing. What I mean by that is, suppose if you take any solid object, right, suppose there is a brick or something like that. Now when this is moving, if you consider just one corner motion or center of gravity of the object motion, it is same as all the particles which are there here. So whether you talk about motion of this corner or motion of this corner or motion of this corner, it is same as far as rectilinear motion is concerned. That is that, because between the point A, if I call it as A, point B, the motion is not existing, right? A is moving, B is also moving, but A to B there is no motion, or A to C there is no motion, or B to C there is no motion. Like that, in solids all the particles will be moving in the same manner, right? If it is a rectilinear motion, every particle will be having a similar motion. If it is a rotation, obviously it will be different rotation, but every particle will be rotating, but there won't be a relative motion between the particles of the object. That is what is what makes the rigid body kinematics simpler, right? But in case of fluid kinematics, which involves motion of all the molecules of fluid with respect to one another, hence it is a complex theory to study, right? As I have told you here, maybe a pipe flow, maybe a river flow, there are many things. Particle which is there here, it will not be going in one plane, it may be going down and then moving up, like that. The particle or the molecule which is there on the top will go down and then again it comes up. So like that, there may be variety of things which will be happening as far as flow is concerned. So when we study fluid kinematics, it will be obviously a very complex study. It will not be as simple as that of rigid body kinematics. That is the point to be appreciated over here. Okay, now there are two approaches for study. Now what are the approaches? These are represented by the names of the people. One is called Lagrange. You might have come across this name in mathematics. So it is called Lagrangian approach. Another one is called Euler, E-U-L-E-R. Euler is the name of person. Again, there is a lot of contribution as far as maths is concerned. So even this person has contributed a lot as far as kinematics is concerned. So this approach is called, put up by Euler, is called Eulerian. Okay, what actually these two mean and which one we are going to study, that we will see. In Lagrangian approach, the behavior and motion of individual particles is observed all along its path. Means, suppose if I take a molecule of the flow over here, and then as if you have to sit on it and go along with it and then see the changes, whether the velocity is increasing, decreasing, it is going up or down, what is the trajectory that is followed, right? What are the pressure changes that are happening. So such a kind of thing, you have to stick to one molecule and move along with the molecule in the flow and try to study that. That is what is a Lagrangian approach. But in Eulerian approach, what he said is a point in the fluid medium is fixed. So what he says is, suppose a particular point, enlarged point I'll do. So particular point at a particular distance or position, everything is fixed, right? A point in a fluid is fixed, and the changes in fluid flow characteristics at that point are studied or observed with respect to, of course, time. In the sense, here if I say the point A over here, so at point A, with respect to time, whether the velocity is changing, whether the pressure is changing, whether the depth is changing, everything that you have to study, right? So fixing a point in a space and then studying fluid flow characteristics, right? Fluid flow characteristics. I'll make this point clear here itself. Characteristics may be velocity of the flow, maybe pressure of the flow, maybe depth of the flow, maybe density of the flow, right? If it is a compressible flow, that is if it is a gas flow, obviously the density will also be changing, right? Pressure will be changing, velocity will be changing. How these factors, how these fluid flow characteristics change with respect to time at a particular point, then it is Eulerian approach. But if you take a particle and move along with the particle and see what is happening to that as it moves, right, that would be Lagrangian approach. Obviously, among these, the easier one would be Eulerian approach. That is what is studied in detail afterwards. Okay. So methods of describing fluid motion in this, fluid kinematics refers to the features of the fluid in motion. So what fluid kinematics means? It is the properties of the features of the fluid motion, fluid in motion. Means the velocity of the flow comes into picture, the trajectory of motion comes into picture, right? The acceleration comes into picture, everything, whatever distance time relationship along with the trajectory, that all comes into this. So fluid kinematics refers to the features or the properties of the fluid in motion. It only deals with the motion of fluid particles without taking into account the forces causing the motion, right? Without taking into account the forces causing the motion. As I have told you, it is geometry of motion with respect to time. That is what is kinematics. Okay. So in particular, now here very clearly said that considerations of velocity, acceleration, flow rate, that is discharge, nature of the flow, and flow visualization are taken up under fluid kinematics. So under fluid kinematics, we are going to study all these things, right? I told you it's velocity, rate of change of velocity, acceleration, velocity multiplied by cross-sectional area becomes flow rate, nature of the flow, how the flow is, and flow visualization. All these things are domain of fluid kinematics. A fluid motion can be analyzed by one of the two alternative approaches called Lagrangian and Eulerian approach. Just now we have seen that. Motion of the fluid is specified by velocity components as function of space and time. So how the velocity is considered, it is not single velocity, but it is component of velocity because it is a space, right? Now when you consider space, obviously we have to talk about x, y, z directions. So the particle will be possessing some velocity, in the sense what is its component as far as x direction is concerned, what is its y direction is concerned, what is its component in z direction is concerned. That is what the analysis is, right? So components of velocity, acceleration components in XYZ directions. That is what is going to be, we are going to study. The Eulerian approach is followed in fluid mechanics. Example, observing the variation of the flow properties in a channel like velocity etc. at a particular section or point is Eulerian approach. Okay. Now velocity of a fluid along any direction, can be defined as the rate of change of displacement of the fluid along that direction. Means suppose there is a flow and the particle has moved from let us say point A to point B in x direction, right? This is x direction. Now it has moved from A to B. This is called displacement, and this displacement dx, right, the change in position is dx, and as occurred in a time span of dt, then dx by dt itself we consider it as velocity in x direction. Velocity in x direction is represented by the letter u, because rather than using the suffixes, it will be better if we use different letters only. That's why we are going to use u for velocity in x direction, v for velocity in y direction, w for velocity in z direction. So here dx is the distance traveled by the fluid in time dt. Velocity of fluid element is a vector which is a function of space and time. So obviously it is a vector quantity. Because of that we will be talking specific directions, right? So when I say u, it is along x direction, right? It is not general velocity, it is a velocity in x direction. So like that, phi if I say, it is a velocity in y direction. W if I say, it is a velocity in z direction. Likewise, the specific notations are there to represent the velocities because they are vectors. So in case of solids, the velocity of the whole body is used to define and describe the motion. I have told you already, if there is a rigid body, it is simple, but however in case of fluids it is necessary to define velocity at every point of fluid flow. So in case of solids, if I take a cylinder, let us say, right, now only one point motion is enough to tell the motion of the whole object. But in this case, suppose if it is a channel flow, right, you cannot just tell one point motion or one molecule motion, right? Motion in all the three directions has to be defined because it may be different in different directions. That is what is said here. However, in case of fluids, it is necessary to define velocity at every point of fluid flow, right? Every point. Okay. So here, this is the way how it is represented. You can just check. There is XY plane, which is a horizontal plane represented by this, right? And then YZ plane, that is a vertical, and ZX plane is also vertical. ZX plane is the white plane. ZY plane is perpendicular to that. Perpendicular to both of this is XY plane, which is a horizontal. So XY is horizontal, XZ is vertical, YZ is also vertical but perpendicular to the earlier plane, right? So now this we say that it is origin O. Generally we say that this point is origin with respect to which we will be putting our reference. Now if I take the point P, if I want to define P clearly, I will be writing P in the bracket. I will be mentioning about X, Y and Z, indicating that P of it is P of X, Y, Z. In the sense, the P is at a position from O at a distance of x, from x-axis at a distance of y, and in the direction of z at a distance of z. That itself I have shown here. Whatever red line is there, that will be indicating from the zy plane the point is at a distance of x, in the direction of x. You can see that rightwards direction is x. So from the plane it is at a distance of x. But how it will be? It will be that way. There it will be shown. You can just see here. That's how it comes. Okay. So that distance is x. Now similarly, there is y distance also in y direction, from that point in y direction, and then from there it will be z direction, and that is that blue line you can just see, that indicates z. Now when we move along x distance, along y distance, along z distance, as indicated by all these components, the p is recognized. So this is position, right? Now in a small amount of time, if the p goes to q, then there will be a motion. This is called displacement, takes place in time. Let us say dt. dt is the time required for motion of ds. Okay. Now the position of the particle is defined by the coordinates x, y, z, as I explained. So position vector represented by p bar or capital P with thicken is equal to xi, yj, zk. X indicates the amount or the magnitude, I indicates x direction, y indicates magnitude, z indicates direction, plus z, k. K indicates again the direction, z indicates the magnitude. The example for this would be, suppose the p is, let us say, something like 5i plus 2j, let us say, and let us say 7k. So what it indicates is in x direction you have to move a distance of 5 along with red, right? And then 2j, in y direction you have to move only 2 units, and in k direction, I mean in z direction, k means in z or z direction, we have to move 7, then we'll be going to the point P. That is what is the position vector. Now displacement from P to Q, ds, you can just see here, ds, it is a actual motion, but again this will be broken into dx along x direction, dy along y direction, dz along z direction, right? So look at that, dx, dy, dz. So now the point P actually has moved from P to Q, but to show that P to Q motion, we have broken that into dx, dy, dz, and this please try to understand here, the actual motion is this only. Actual motion is from P to Q, that motion, but for the sake of study, that ds is broken into x component, y component, and z component. So ds, you can just see here, ds is a dxi, in x direction amount of dx, in y direction amount of dy, in z direction amount of dz. So that makes ds. So actual motion is this, but it will be treated as motion in x direction with an amount of dx, motion in y direction amount of dy, motion in z direction and dz, right? This occurs in dt. Then yeah, same figure is over here. Then velocity component in x direction, which I have told you we are representing with separate letters, and that is u, will be dx by dt, right? So this velocity, the total velocity, if I want to write this velocity v, I should write this as ds by dt, because ds is the distance traveled in an amount dt. So ds by dt is nothing but velocity v. But if we say only in x direction, then it will be u, which is dx by dt. Similarly, in y direction, the velocity is represented by v. The amount of motion is dy in a time duration of dt, that's why dy by dt. And in z direction, w, dz by dt. The total velocity will be sum of all the three. So it will be v, the resultant velocity, is equal to ui plus vz plus wk. U is magnitude, I is the direction in x direction, phi again magnitude in y direction, w is again magnitude in z direction. So if you want to find out total magnitude of the velocity, it will be equal to square root of u squared plus v squared plus omega squared. You know that. Now for example, here itself dx dy, what is the total distance? I want to calculate this. This will be square root of dx squared plus dy squared. Now with this and this, if I want to calculate ds, again ds will be square root of dz squared plus square of this, which will be nothing but ds, exactly in the similar manner. So if I want to find out ds, I will have to magnitude ds it is. So if you want to do that, you have to do square root of dx squared plus dy squared plus dz squared. Okay. Similarly, magnitude of velocity is v magnitude will be equal to square root of u squared plus v squared plus omega squared. Okay. The motion is characterized by its velocity of flow. Okay, motion of fluid is characterized by its velocity. Velocity is the major indication of fluid flow. Of course, other properties are also there, like pressure, like density, right? The flow characteristics can be velocity, density and pressure at the point of consideration. So that's important. Flow characteristics can be considered at any point, but here I have considered u equal to dx by dt. You can consider pressure in x direction, px equal to dx by dt. So like that, increment of pressure in x direction or increment of velocity or increment of density. So likewise, whatever we are studying velocity, in the similar manner other characteristics can also be studied. So it is not only velocity that we will be studying, all or any property of motion can be studied with a similar approach. As fluid particle moves in space, its velocity depends upon x, y, z and time, right? So when the particle moves, obviously it depends upon what is the x direction, what is the y direction, what is the z direction and how much is the time. So it is dependent on four parameters. So I can say the u is a function of x, y, z and t, because it is a three-dimensional flow. It is not just only one, but we are looking from the angle in x direction what is happening, right? Then I say it is dx by dt, but it is a dependent variable which depends upon all other factors like y, z and t, right? Similarly, the velocity v, which is velocity component in y direction, is function of x, y, z and t. Omega is a function of x, y, z and t. So for three-dimensional flow, the velocities are like this. Suppose if we are talking about only one-dimensional flow, for example x and y only and z is not there, in that case the z will not be there and u will be a function of x, y and t. Similarly, if it is a one-dimensional flow, it is function of x and t only, right? Okay, we'll go further. Okay, here I have shown a flow, right? Based on various aspects of the the flows are classified as, here there should have been a comma, based on various aspects the flows are classified as below. What are the flows? Types of flow: 1, 2, 3, 4, 5. This is how the types of flows are classified: steady, unsteady flow, uniform, non-uniform flows, 1, 2 and 3 dimensional flow. The flows can be laminar flow and turbulent flow, or they can be rotational flow and irrotational flow. So all these 5 types of flows would be there. Of course, there will be overlap of classification. This classification is not quite independent or exclusive classification. The flow that you call it as steady or unsteady can be laminar or turbulent. Like that, there will be some overlaps possible, especially 1 and 2, 1 and 3, or 2 and 3. Like that, there will be a lot of combinations which are possible. Okay. Okay, here steady flow means what? I have defined here. Steady flow definition is, if the various flow characteristics. Now, what are the flow characteristics? Again, I tell you, flow characteristics are nothing but velocity, pressure, density, depth. So these are the flow characteristics which will be changing with respect to time. So these things, how they vary, that is what is the point of study. Now, if the various flow characteristics such as velocity, pressure, density, etc. do not change with respect to time, then it is steady flow. Okay. So how it is represented, you can just see here. The velocity with respect to time, dou u by dou t, that is partial differentiation with respect to time of u. The velocity is not changing in x direction with respect to time. It is equal to 0. The velocity in y direction with respect to time is not changing. The velocity in z direction or z direction with respect to time is not changing. The pressure is not changing with respect to time. The density is not changing with respect to time. So change with respect to time, that is what is differentiation. So dou u by dou t equal to 0. Similarly, all this up to dou rho by dou t. Rho is density, p is pressure, uv, omega or upw are the components of velocity. Now all of them are equal to 0. All of them are equal to 0. Represent that it is steady. Steady means there should not be any change with respect to time at a particular point. Okay. Now suppose the flow is occurring and I have points of reference as A and B. So A and B, when I consider, there are 2 points in space. But what I'll talk now for defining steady only about 1 point. And then let us say at time t1 the velocity is va1. You can assume some values for this. For example, now the time is, let us say 12 o'clock. At 12 o'clock the velocity is 5 meter per second, let us say, right? And then after some time, at time t2, which is t1 plus delta t, maybe after 5 minutes, after 10 minutes, after 1 hour or so, means if I consider it as 12:30 and then see what is the velocity here, then phi at A only, but at time instant 2, VA2 is found to be equal to VA1 only, means it has not changed all along, let us say, right? The velocity is not changing as the time passes at a particular point. Then this indicates it is a steady flow, right? So that is a steady flow. Now why it is shown as d phi by dt? The phi represents all the characteristics of the flow, right? Rather than telling u, v, omega, p, rho, etc., you represent all of them by a single letter phi or phi. The phi represents any fluid flow characteristics, and fluid flow characteristics are velocity, pressure, density, etc. So if the fluid characteristics are not changing with respect to time, in the sense d phi by dt with respect to time, there is no change equal to 0, then it is a steady flow. Similarly, unsteady flow in the sense it is not equal to 0, just the same thing, but it is d phi by dt is not equal to 0, then it is unsteady flow. Here the flow characteristics change with respect to time. So any one or all of them can change. Not necessary that all of them should change for making the flow unsteady. To make the flow unsteady, any one of them is non-zero, then also it is fine. Means dou u by dou t equal to 0, dou v by dou t equal to 0, dou omega by dou t equal to 0, dou p by dou t equal to 0, but dou rho by dou t is not equal to 0, it has got some value. Then though all these values are equal to 0, because this one is not changing, it is unsteady flow, means the pressure is not remaining, density is not remaining the same all along the time, density changing with respect to time, then we say that it is unsteady flow. Okay, here it is uniform flow or non-uniform flow. There are two things here. Okay, here when I say uniform flow, the flow characteristics describing the flow do not change both in magnitude and direction from point to point in space. So here when I define uniform flow, I am considering space. When I talked about steady and steady, I stuck to one point, and then at one point with respect to different time instants, what is happening, that is what is observed, right? In this case, with respect to two different points, I am trying to study the things. And then let us say at time t1, like I told you, let's say it is 12 o'clock, and then 5 meter per second is the velocity in at point A, and then at point B at the same instant, right, t1, the velocity is vb1, and let us say at time t1 both vb1 and va1 are same, in the sense at the time of 12 o'clock the velocity at A is 5 meter per second, velocity at B is also 5 meter per second in the same direction. Means the velocity over here, the velocity over here, if you compare, it is not changing. Point to point, if you go on changing here and there in space, the velocity is not changing. Means fluid characteristics is not changing. It is remaining the same, right? In such case, we say that it is uniform flow, right? So rather than just velocity, you can consider it as phi, d phi, but not with respect to time. Now the change is with respect to space. So change of fluid flow characteristics with respect to space, d phi by ds is equal to 0. There is no change. Point to point, at different points in space, different points in plane, or different points along a line, if the flow is occurring, and if you consider at two different points, if the fluid characteristics are not changing, then it is considered as uniform flow. phi is any fluid flow characteristics, and this is considered at one point, one instant of time. Means if I am talking about 12 o'clock at different points, not that this is at 12 o'clock 5 meter per second, this is at 12:35 meter per second. No, you cannot compare. At the same instant of time, but at two different space points, if the fluid characteristics are same, then it is uniform flow. Otherwise, it is a non-uniform flow. Non-uniform flow, here the flow characteristics change from point to point in space at any instant of time. Okay, the phi represents any fluid flow characteristics like velocity, pressure, density, etc. Now for this we can write d phi, it is missed, d phi by ds means fluid flow characteristics change with respect to space is not equal to 0, in the sense there is a change, right? If it is the change is 0, in the sense there is no change. Here there is change is non-zero, in the sense there is a change. So non-uniform flow is represented by d phi by ds is not equal to 0. So uniform flow is d phi by ds is equal to 0. I think with this we'll stop here. We'll consider the other things in the next class. Thank you.